So in the next problem, we start with knowing that a fair coin is tossed twice. So we're going to toss a coin, then we're going to toss it again. We're going to find the probability for each of the following. And a lot of times people will struggle with at least and at most. And so right above this, I made a note on your notes that at least one means one or more. At least two means two or more. At least three means three or more. At most one means one or less, 0 or 1. At most two would be 2 or less. At most three would be 3 or less. And I always kind of just put myself, when I see a student struggling with this vocabulary, if I say, if a student says, I don't know what at least one means or at least two, and if I said, okay, I have enough money to pay for at least two of you dinner, and I put it into that perspective, they start understanding it a lot better. If I say I have at most enough money to pay for at most two of you, they know that I can't pay for more than two of them. And so with this vocabulary, you could always make an anchor chart, put it up on the board, and then relate it to a real life scenario, and it's going to help them understand that. Now, if I'm thinking about tossing a coin twice, a lot of students will absolutely miss this because they won't consider the sample space. And so before ever starting this problem, I would have the students rewrite the sample space of everything that can happen if you flip a coin twice. And some of them might need that tree diagram that we drew previously in this lesson, but regardless, we're going to rewrite that sample space. You can get heads and then heads again. You can get heads and then tails. You can get tails first, then heads, or you can get tails first and tails again. And these are the 4 outcomes you can get when you flip a coin twice. So looking at this sample space, now it's much easier to answer these questions. So what is the probability that we get exactly, and I am so sorry, this pen is not writing well on my screen, but we're going to get it done, exactly 1 tail. And so out of these 4, I look, and these 2 outcomes have exactly 1 tail. So that's going to be 2 out of 4, which will obviously reduce to 1/2. 2 outcomes have exactly 1 tail. The next one wants the probability of at least 1 tail. And so at least, we can come up here and look at that, means one or more tails. So at least 1 tail, this has at least 1, this has at least 1, but this last outcome also has at least 1 tail. It has 2 actually. So the probability of getting at least 1 tail would be 3 of the outcomes out of the 4. And then the final one here, the probability of at most 1 tail means 1 or less, 0 and 1. So at most 1 tail would be, and I'm going to switch colors here, at most 1 tail, this has at most 1, this has at most 1, this has at most 1. At most 1 tail means 1 or less, and this last one does not. So the answer again is 3 of them out of 4 of them have at most 1 tail, none or 1. If we move on, we're going to go into some more definitions, and this is going to be on your homework, this is going to be on your exams. So an event that's impossible is an event that cannot happen. And the example I give you here is rolling a 7 on a standard dice. There is not a 7 on a standard dice, so the probability of that happening is 0. And so on your homework, I'm going to ask you, what is the probability of an impossible event? And that answer is 0. And if a probability is 0, then you need to know that that event is called impossible. So if something absolutely cannot happen, the probability of it happening is 0. It is impossible. If an event is certain to happen, then its probability is 1 because 1 is equivalent to 100%. So the probability of rolling a 1, 2, 3, a 4, or 5, or a 6 is 1 because if you roll a dice, you're for sure going to get one of those 6 outcomes. That is 100% going to happen, and that event is called certain. Now, if you think about this, the smallest answer that a probability can be is 0. The biggest answer that a probability can be is 1. And all of your other probability answers are going to be between 0 and 1. And you can see, like, we've just gotten answers like 1/2, 3/4. All of those falling between the numbers 0 and 1. 1 being equivalent to 100%. So 0, there's no chance of this happening. 1, it's for sure going to happen. And every other probability answer is between the 0 and 1. Next definition is mutually exclusive. These are events that have no elements in common. For example, if we roll a dice and then, let me just go off of the example that I have written. Rolling an odd number and rolling an even number are mutually exclusive events because they don't have any elements in common. If I were to roll a dice and then flip a coin, those two events have no elements in common, therefore they're mutually exclusive, meaning none of their outcomes overlap. And we will have some probabilities where the outcomes do overlap, and so it's very important to understand that mutually exclusive means it's two events that have no outcomes in common. Complements, we learned the word complement in Math 1350 when we were doing sets. And if you recall, in 1350, we had this example of a Venn diagram. And inside here, this represents all of the people that live in Lubbock, and it was in a set. And then out here was L complement, representing all the people that do not live in Lubbock. And so when we do the complement of a set, and let's just go ahead and read it before I get ahead of myself. Two events, which are A and not A, meaning A complement, comprise the entire sample space. The event not A, written A complement, is the complement of A. Example, let A be the event of rolling a 1 on a standard dice. So the event A is 1. A complement would be all of the outcomes of rolling a dice that do not include 1. And so another example of, one of these events is let A be the, event of drawing an ace out of the deck. Well, there's 4 aces in the deck. A complement would be all of the other 48 cards that are not the aces that are in the deck. And so the reason this can be so helpful is because if I find the probability that we get a 1 on a dice, that's 1 out of 6, the probability of A complement would have to be 5 out of 6 because the two together have to make one whole. And so if you know the probability of an event happening, it makes it much easier to find the probability of the complement of that event happening, knowing that the two together come together to make one whole. All right, let's just review a little bit of our notation for sets before we go on and do any more problems. So the empty set it's like a 0 or an O with a slash through it. The upside down U, recall, means intersection. That's the overlap, A and B. Union is when we put the two together. A union B means A and B union together, anything in A or anything in B, pulling the two together. And if they are mutually exclusive events, then they don't have anything in common. Remember, there's no overlapping outcomes in common, so the intersection would be the empty set. So we're going to keep that in mind as we look at these properties, and some people get kind of ooged out by the notation of these, but this is all stuff that we've already talked about. All the first property means is the probability of any event that we're going to do in this class, in any event in this world, the probability of anything happening, the answer has to be between 0 and 1, including it can be 0 and 1. If it's impossible, it's 0. If it's certain, it's 1. And every other probability answer is between 0 and 1. The next property is the probability of A or B means the probability of A happening and the probability of B happening added together. Because if A can happen or B can happen, then it makes sense that we would add the two together. The problem is if they're not mutually exclusive. And so right here, if they have nothing in common, like what's the probability of, rolling a 2 or flipping heads. I mean, those have nothing in common. If they have nothing in common, you're just going to add the two together because they're exclusive. They don't have any outcomes in common. But there are times that outcomes can overlap. So if I say, what is the probability of rolling a diamond? Let me get my vocabulary correct. What's the probability of drawing a diamond or drawing a queen? And I'm going to pull up an image of all the cards just to point out what I mean. Okay, so I said, what's the probability of getting a diamond, which would include these 13 cards, or getting a queen, which would include these 4 cards? Well, if you notice right here, this one card is an outcome in both of those. It's a diamond and it's a queen. And so what happened is, if we do the probability of a diamond, that's going to be 13 out of 52. If we do probability of a queen, that's going to be these 4 out of 52. Well, this card right here got counted twice because these two events are not mutually exclusive. They have this one outcome here in common. And so what your notes is saying to you is, if you're doing A or B, you're going to add the two together, but you have to subtract out anything that was counted twice, basically. It was counted in both of those sets. So you remove any element that was contained in both of those. And since we have the cards open, we'll just look at another example. So on the deck of cards, what if I said, what is the probability of getting a red card and a 10? Well, the red cards would count all of these 26 cards, and the 10s would be these 4 cards. But if you notice, these two 10s got counted in red and 10s, so it would have to be subtracted out because it was counted twice. And you'll notice that as we do some of the questions, you'll see the overlapping, you'll see how we remove it. But it's really easy if you understand that we're just removing anything that was counted in both of the two events. On part C, we've already talked about this. If we find the probability of something happening and the probability of it not happening, those two answers should always add up to 1. And so if you recall, we did, what's the probability of getting a 1 on a dice? That was 1 out of 6. The probability of not getting a 1 on a dice was the other 5 out of 6. And those two answers do add up to 6 over 6, which is 1. If an event cannot happen, if the probability of it happening is 0, then that is called impossible. If something is going to happen for sure, the probability of it happening is 1, and we call that a certain event. The last thing we're going to talk about is there's no special formula for the probability of A and B. You just count the number of outcomes that are in both A and B. And so we point that out because A or B means you find the probability of A, you find the probability of B, you add them together because it can be in either one. But A and B means all of the elements that are in A and in B. And so, if I say, what is the probability of getting a red 10? Red 10 is 2 outcomes. Let me get back to that image. A red 10, here's all the reds, here's all the 10s. So there's 2 cards that are red and a 10. And so the word and definitely means different than the word or. If I said red or 10, that's all the reds, and you would add to it all of the 10s. So the word or and make a difference in how you work the problem. All right, let's work a couple of more problems in this video, and then we'll pause this one and move on to a 4th video. So a box contains 3 red balls, 4 blue balls, and 5 green balls. Suppose one ball is drawn from the box. Find the probability that the ball is red or blue. So we're going to keep in mind that the word is or. So I want the probability that we get a red or a blue. And if we look up above, when it's or, what we're going to do is we're going to find the probability that we get red, and we're going to add to it the probability that we get blue. And a lot of times after a while, people just kind of combine these steps and do it all in their head. So the probability that we get red is 3 red out of how many total balls? So we have 3 and 4 is 7, plus 5 more gives me 12 total balls. So 3 out of 12 are red. Blue is going to be 4 out of 12. And so the probability of getting red or blue is 7 of the balls out of the 12 total. If there's ever any outcomes in common, that's when you would remove those, but there's not any overlap in the red and the blue balls. So it's just the red ones plus the blue ones. Next we have a spinner, and it asks us to shade region 1. I'm going to get a lighter color here to do this. So here's shading the first region. And the following spinner is spun 1 time. Find the probability of landing on an even number or a shaded piece. So we want the probability of landing on an even number or a shaded piece. So that's going to be the probability of an even, and then we would add to that the probability of a shaded. So we have sections 1, 2, 3, and 4. The probability of spinning and landing on an even number is 2 of the outcomes out of 4 of the outcomes. The 2 and the 4 are both even. Plus, there's 1 shaded section out of the 4 sections. So if I want the probability of landing on an even or a shaded, that's going to total to 3 of the sections out of 4 of the sections. And notice again, there wasn't any overlap in what was even and what was shaded. So those 2 events are mutually exclusive. And then let's do one more example in this video, number 12. This time it asks us to shade section 2. So that we just need to remember that had a 2 on it. And again, I want to do the probability of landing on an even or a shaded. So we're going to do the probability of an even number. The even number is the 2 and the 4, so that's 2 sections out of 4 sections, plus the probability of the shaded, because or means add. So there's 1 section shaded out of 4. But if you notice, this section here got counted in both. It was even and it was shaded. And so we have to remove anything that got counted twice, which gives me 2/4, which would reduce to a half. And so if there ever is an outcome, because these are not mutually exclusive, even is 2 and 4, shaded is 2. The 2 is counted in both of those events, and so that outcome got counted twice, which is why it had to be removed. And so if you ever have an outcome that gets double counted, however many of those outcomes there are, you have to subtract those out.